All right, so this is the first of several lessons. I'll focus on curve sketching, which I mean really was introduced last day. And I'm going to front load with a number of just concepts or tests here. First derivative tests and second derivative tests and concavity tests. All these things I'd like to explore in more interesting detail in group problems in class, but I'll kind of cover the basics here. So suppose C is a critical number at some point of a function. Can't remember, a critical number means, or a critical point is where the derivative is either 0 or does not exist. And that's just one of the ideas introduced last day. Well, there's kind of three possibilities if we have a critical number in terms of looking at the derivative. One of the possibilities, this first point, is that f prime, the derivative, changes from positive to negative. And the idea is we're looking from left to right. So the derivative changes from positive to negative. And if that's the case, then that point C is a local maximum. So let me explain why that must be. If we just kind of move over here. If we have a derivative that changes from positive to negative, well, a positive derivative means the slope is positive, which means the function is increasing. So something like this. Okay? A negative derivative means the function is decreasing. So something like this. And so it doesn't really matter how the shape of these particular curves are or whatnot. If this is the point where a derivative changes from being positive to negative, then that must be a local max. It may also be an absolute maximum. We can't tell that just from what I've stated here, but there's no way it can be anything else. It has to be a local maximum. And so notice if it's the other way around, if we go from a derivative being negative to positive, no matter how it looks, that must be a local minimum. So if f prime is negative or if f prime is positive, and that's the sort of change at some critical point, then that must be a local min. And the last example, I'll erase all this, is what if the sign doesn't change? It's still a critical point, but the sign doesn't change. It's still positive on both sides or negative. Well, one example would be something like this. There's a critical number right there. The derivative right there is 0. But notice on the left-hand side, the function is increasing. So the derivative is positive. On the right-hand side, the derivative is increasing. So the function is increasing, so the derivative is positive. It's just at that instant the derivative was 0. And this is neither a max or a min. And if, in something like this, we call it an inflection point. And we'll talk more about inflection points later on. So everything I've stated there is what's kind of summarized right here. This inflection point, though, which is a phrase that's going to come up later, that's only if what I have here is stated is true, and that's the the second derivative is also equal to 0. And I'll talk about second derivatives in just a moment. So concavity has to do with second derivatives. And so before I talk about these points, let me slide over here again. Something like this is considered concave up. Something like this is considered concave down. Essentially, if it kind of opens up, it's concave up, opens down, it's concave down. Although the only problem with that is, for example, an exponential function like this is concave up, even though it's not really opening up like a parabola does. And, just this region, I don't know, just that region there, we say is concave down. So that's it. Let's go to I'll go to simpler examples. Oh, why does it keep going back there? There we go. So concave up. So if something is concave up, then the second derivative must be positive. Okay? So let me talk about that. If this entire interval I've sketched out, which is concave up, all along this interval, the second derivative must be a positive number. So let's think about what that means. The second derivative is how the first derivative changes. Okay, so I have a critical point right here. Okay, that doesn't really matter. If I look from left to right, what's happening first to my first derivative? My first derivative here is negative. And once I get to this side, my first derivative is positive. Okay? Not only that, though, if we look from here to here, the derivative, although it changes from negative to positive, is getting larger the whole time. For example, in this region right here, the derivative is negative, and it's fairly steep. And the closer I get to here, the derivative is still negative. It's still going down, but it's less steep, which means it's still a negative number, but it's closer to 0. At this instant right here, the first derivative is 0. And now the first derivative is positive. Just barely, but positive. And the more I go to the right, the steeper and steeper the function gets, which means the larger and larger the first derivative gets. So you think about everything I just said, the entire time the derivative kept getting larger. The entire time as I went from left to right, the derivative kept getting larger. The derivative kept increasing. And if the derivative is increasing, that means the second derivative is positive. And that's concave up. And the other way around is concave down. If I look at this, over here, the function is increasing. But as I get farther and farther to the right, it's still increasing, but by less and less, at less and less rate. Which means the derivative is getting closer and closer to 0. It's still positive, but it's getting closer to 0, which means the derivative is going down. Roughly around right here, the derivative is exactly 0. It's a critical point. And now the function is decreasing, just barely, so it's a negative number, but close to 0. And the farther I get to the right, the steeper and steeper it's decreasing, which means the second derivative is getting, the first derivative is getting more negative, which means the entire time as you went from left to right, my derivative was getting smaller. So it went from this way, my first derivative was shrinking. First it was positive, then it was negative. And if that means my first derivative was decreasing, and my first derivative is decreasing, that means the second derivative is negative. Like I said, I'd like to discuss these things in person. But with that said, that does cover the basics of concavity. And that's what I've summarized right here. If your second derivative is positive, it's concave up. If your second derivative is negative, it's concave down. And as stated up here, if your second derivative is 0, it's an inflection point. And so now we can see that an inflection point is where a function changes from concave up to concave down. For example, if I sketch something like this, hopefully you can visualize roughly where this function changes from concave up to concave down, or concave down to concave up. This is clearly concave down over here. This is clearly concave up over here, which means somewhere in here there must be a point where it switches from concave down to concave up. It's, let's say, roughly right there. And we call that an inflection point. And so that's it. Where is that inflection point exactly? I mean, I have a rough visual. I can't actually say exactly where it is unless I knew what this function was in the equation, and then I found the second derivative. But I can see it's roughly around there. Okay, I mean, it's definitely not right here, right? It's definitely not down there. So it's somewhere in there is that inflection point. And that's where your second derivative equals 0. So in this particular example here, everything I've highlighted in yellow, this is concave down. So second derivative is negative. Everything I've highlighted in blue is concave up. So my second derivative is positive. Lastly, let's say you know a function has a critical point in some region, and you know the concavity there. So let's say, for example, I look right here, that point in orange. That's a critical point. If I don't know what the graph looks like, but I know there's a critical point, and I know it's in a region where the second derivative is positive, that means I know there's a critical point in a region that's concave up, which means this must be a local min. Anytime you have a critical point in a region that's concave up, it'll always be a local minimum. And again, if it's concave up and there's a critical point, it can't be a max. Because if it's a max, let's say right here, if there's going to be a maximum in some region, it has to be a region that's concave down. So what I just stated there is what we call the second derivative test. It's connecting critical points to second derivatives. And that's what it states here. So suppose the second derivative is continuous near at some sort of critical point. So if the first derivative equals 0, this is a critical point, and the second derivative is positive, that means we have a critical point in a region that's concave up. And if you have a critical point in a region that's concave up, it must be a local min. And it's the other way around. If you have a first derivative that's positive and the second derivative is negative, that means that region is concave down, and that means that critical point must be a local max. Okay, a lot of ideas front-loaded here. Let me erase my little mess over here. Who cares? Let's kind of continue with this sort of ideas we saw yesterday, which is piecing together various information about functions, now strictly in terms of derivatives and limits, and see if we can visualize what this function looks like. I have told 3 questions similar to this. For each of them, I would try it on your own. That said, maybe the first one, you just want to watch the first one. But for each of these, the more you try on your own before you see me work it out, the better. That said, if you are going to try this on your own, I have, 6 conditions about a function, and we want to sketch something that satisfies all these conditions. All right. So, assuming maybe you've paused it, maybe not. The first derivative is positive from negative infinity to 1, and the first derivative, the first derivative is negative there, and the first derivative is positive from 1 to infinity. So the first thing I'm just going to do, there's various ways of looking at this, but I'm just going to set up a simple little xy axis. And so far, 1 is definitely an important number, positive 1. So I'm going to put a little 1 right here. And I know that's a point between where a function is increasing or decreasing. And so if I want, let's say I could start by saying draw something like this, where the function's increasing, something like this, where it's decreasing. But also, I want to be willing to make adjustments to this. OK, but for a quick little sketch, let's say right there, I can obviously make adjustments. That's so far fitting the bill of those 2 constraints. The first derivative is positive on the left of 1, and it's negative on the right. OK, next. The second derivative is positive between negative infinity and 2, and positive 2 infinity. So that's it. Let me just show, let's kind of sketch. Negative 2 is an important point here, positive 2. And that region here is where this function has a second derivative that's positive, so this must be concave up here. So less than negative infinity and greater than positive 2. Sorry, less than negative 2 and greater than 2. So that's from sort of this region here and here. It should be concave up. So now, OK, let's take this now and imagine it's looking like this. Now, actually, I'm going to do something that's wrong. OK. I know this can't be correct. Although this region here is now concave up, and this region here is concave up. The problem with what I've drawn is I've just drawn more critical points now. And the only problem with that is that means right here, my function is increasing again. Wherever this number is, wherever I drew that critical point, to the right of it, my function is definitely increasing. If my function is increasing there, that means the first derivative must be positive after this mysterious point. But we know that's not the case. We know my function is increasing only from negative infinity to 1. So there's an inflection point at 2 and negative 2. So it does change concavity, but it doesn't go exactly like this. OK? So I'll leave this for a moment. And both sides have a similar problem. But I know this can't be right. OK? What about here? The second derivative is negative from negative 2 to 2. That means my function is concave down from negative 2 to 2. Well, that's what I've already drawn. Great. So that I don't have to adjust anything. So then I have some limits. The limit as I approach negative infinity for this function is negative 2. So we haven't talked about this in a while, but we did talk about this in our limits lesson. If we have a limit going towards infinity or negative infinity, and it equals a number, that means there's a horizontal asymptote there. So I now know this function has a horizontal asymptote at negative 2. OK, so let me draw a negative 2 on my y-axis. And I'm going to show this. So as I go to the left forever, there's a horizontal asymptote, which means now I can see what happens here on the left. I can see my function at this inflection point right here. It becomes concave up, but if there's a horizontal asymptote, it never actually, it's always concave up, but it never actually curls and starts literally going up. So what I've sketched there does fit the bill. It's concave up, but it never has another critical point, which means I can erase this, and I can now see what's kind of happening here. And then similarly, this last point here, as I approach infinity, positive infinity, the function equals 0, which means there's another horizontal asymptote right here, right on the x-axis. And the same idea. If I erase now this region here, I still have an inflection point at positive 2. It's still going to change from concave down to start being concave up, but now I can see there's a horizontal asymptote right here. And so now, if I look at all this, I believe it has everything we need. It's concave up less than -2. It's concave up greater than +2. But if we look at my very first two constraints, the function is increasing all the way from -infinity up to 1, and it is, and it's decreasing from 1 all the way to infinity. So I didn't, a common mistake is we create extra critical points. And there we go. There's my function. Okay, I'll just label it y equals f of x. All right. While there's some variations you can have on this, not a lot. I mean, if I add a little squiggle right here, just to be creative, I've just created another critical point, which means the derivative has changed in a few places. And again, so there's not a lot of variation that's possible here. All right, so the next one, I highly encourage you to try this on your own. Have you tried it on your own yet? So again, the key to this is have a pencil or have a whiteboard or have something that is easy to change. That's it. I got a lot of constraints here. Okay, so I'm going to do something similar as before. I'm going to sketch out a little x and y here, and I'll start to label points. So first, f prime does not exist at 0. Okay, so right at the origin, my derivative does not exist. Okay, that's it. I can't really draw much more than that. I can tell the origin's right at 0. I don't need to label that. What's my next point? F prime at 4 equals 0. So when x is 4, say right here, the derivative is 0. So if the derivative is 0, that means I have a critical point there. And I'll just draw it above here for now. So I know it looks something like this, or it looks something like this. That's how long I can have a derivative of 0 right there. And so I'll just leave that for now. I may want to change it. I mean, if they give me more information. For example, there's nothing telling me it has to be above the x-axis. It could be right on the x-axis. Next, the first derivative is positive, which means it's increasing on the interval from 0 to 4. So from here to here, it's increasing. Okay, something like that, for example. What's next? The first derivative is decreasing from -infinity up to 0 and from 4 to infinity. So first, from 4 to infinity, it's decreasing. So I'll draw something like that for now. But also, from -infinity up to 0, it is also decreasing. So it can't look like this, because that's increasing as we look from left to right. So maybe something like this. And that said, notice, if I draw something like this, right at 0, I have a cusp, or a corner. And right at 0, my first derivative does not exist. So this actually works quite nicely if I draw it like this, because this kind of connects back to the very first constraint we had. F prime at 0 does not exist. Okay, next, second derivatives. The second derivative is positive from 6 to infinity. So that means right here it is concave up. From 6 to infinity. So let me draw a 6 roughly, I don't know, about right here. So now right around here, it becomes concave up. So I'm going to adjust this part here and maybe have it go like that. But again, if I start going around like this, I've created another critical point, which I'd rather not do unless I know there's another critical point. So I'll just kind of leave it like this for now. Okay, but now it's going concave up. And that's kind of what I see right here, concave up. The second derivative is negative, which means it's concave down from negative. There should be a bracket right here. From -infinity to 6. So it's concave down. All of this region is concave down. Well, that's actually what I have here. If you notice what I've drawn, all of this is concave down. All of this is concave down. Everything there is concave down. So hey, that's nice. That's what I've already drawn. Lastly, I have these limits. So as I approach infinity, as I approach -infinity, the limit of the function is infinity. Sorry, I think I said there's asymptotes, but no, there's not, because the limit as we approach infinity is infinity. So all that means is my end behavior is going up. And so as I approach -infinity, my function gets infinitely large. So I just want to adjust this slightly, because it looks like my graph is kind of flattening out over here. It doesn't. It just keeps going up. So maybe something like, there you go. That works. Okay, as my function as I approach negative infinity, the output approaches positive infinity. And if I look at the last constraint, as I approach positive infinity, the limit of the function equals negative infinity, which just means as I go forever to the right, my function goes down forever. And so I got to be careful here, because if I draw something like this, it's now concave down greater than 6, and we know it should be concave up. So how can I draw that? Well, for example, if I just go something, it's almost becomes linear-like. For example, something like this. There we go. It is concave up, but it is still going down forever. And so if I just kind of draw this now without a highlighter, I don't know, something like this. We have a cusp right there, so the first derivative does not exist. We have a critical point there, an inflection point there, and then concave up, but still going down forever at 6 onwards. And again, there's my inflection point. And notice again, at 0, my first derivative does not exist, as stated. All right, so the last one, same idea, but I've given you some derivatives and, well, equations. I've given you the function, the first derivative, and the second derivative. They're all given for you. But our goal in the end is kind of the same thing. It's to sketch a graph of f of x. And in the and we'll end up performing a similar sort of task as we did before. So that said, unlike before, I don't have all these little characteristics given to us. We have to basically find them ourselves. And so what I have here is a series of points series of steps that we probably want to follow. All right, but notice in the end I want to sketch f of x, and I'm giving you the first derivative and I'm giving you the second derivative. Although you could figure those out on your own, use the chain rule, and quotient rule probably to go from the first to the second, but they're already done for you. Okay, so first, what's the domain of function f? If I look at function f, here's my function right here. You know, I could also write this as x times the 5th root of 1 minus x all squared. Or I can imagine the power of 2 being outside of that radical. In the end, though, x can be any number. Again, a 5th root, you can have any odd numbered root. You can find the root of you can find the 5th root of a negative number, plus you're squaring it anyways. But again, the domain I can see is all real numbers. And so that means I know this function, again, goes on forever to the left and the right. That's important. So the domain is all real numbers. At some point, if we want to visualize what a function looks like, thinking about the domain is pretty critical. Okay, so I know this function has a domain of all real numbers. Next, I want to find the critical points. So if I want to find the critical points, I want to find where my first derivative equals 0 or does not exist. So if I want to find the critical points for f of x, let me first start where my first derivative equals 0, and then I'll think about where my first derivative does not exist. Well, I can just look at my equation up here. For the first derivative, it'll equal 0 where the numerator will equal 0. And the numerator will equal 0 at 5/7. I could just solve for 0 for the numerator. And that's the only place. Because my denominator, if I make my denominator equal 0, the whole thing will be undefined, which I can get to in a bit. But that, again, if I want to make this rational expression or this fraction all equal 0, I have to make the numerator equal 0 and not the denominator. And so again, the only way that's going to happen is when the numerator is equal to 0, so when x is 5/7. And so right here, x equals 5/7 is the only place. What about where it does not exist? Well, looking back here, my first derivative will not exist when I'm dividing by 0, which I can just see quite clearly when x is 1. So when x is 1, my first derivative does not exist. Although again, function f has a domain of all real numbers. Okay, so just the first derivative does not exist at 1, but my function is still defined at 1. All right, so right here, I can say when x equals 1 only. And those are my critical numbers. If I find the y value, I can call them critical points. But either way, that's pretty important. Okay, so next, I got that part done. Determine where my function is increasing or decreasing. Or, I mean, I don't have to do these in order, but I might as well. So where's my function increasing or decreasing? So I'm going to make a little number line here. I'm not going to go to a sketch of a graph yet. There's too much for me to think about. But my function, if I have only two critical numbers, that means my function, in terms of where it's increasing or decreasing, I only need to pay attention to those 2 points, 5/7 and 1, which are very close to each other. 5/7 is 2/5 away from 1. So these are, again, and when I do want to sketch this out, I need to realize these are probably quite close to each other. And I know that this is where f prime equals 0. This is where f prime does not exist. So now, how do I figure out if it's increasing, decreasing, increasing? I have a few options. One option is to pick a number, for example, for this region here. One option is to pick a number less than 5/7. How about 0? And just take that 0 and put it into the first derivative. And if I get out a 0, sorry, if I get out a positive number, it's concave up. If I get out a negative number, it's, oh, sorry, I distracted myself. Take 2. One perfectly great way that I'll just do to find where this function is increasing or decreasing is to pick a number in this interval, somewhere anything less than 5/7, because I know there's no other critical numbers less than 5/7, and put that number into the first derivative. If I get a positive number out of my first derivative, I know it's increasing. If I get a negative number out of my first derivative, I know it's decreasing. If I get a 0 out of my first derivative, I know I made a mistake somewhere, because there's only two critical numbers here. 5/7 is the only place where my first derivative will equal 0. So if I just look here by inspection, if I make x equal to 0, make that a 0, make that a 0, any number less than 5/7, but 0 is pretty nice, I can see I get 5 in the numerator, or more importantly, I get a positive number in my numerator. Because all I care about is my derivative positive or negative. And down here, I have 1 minus 0 to the power of 3/5. Well, that's going to be a positive number times 5. That's a positive. So when x is 0, which means, or really when x is any number less than 5/7, my first derivative is going to be a positive number divided by a positive number, which is a positive number, which means I know my derivative is positive when x is less than 5/7, which means I know my function is increasing in this interval. And again, I didn't actually evaluate what it was. Is it positive or negative? So next, let me look at this region right here, between 5/7 and 1. Again, I can do whatever I want. I'll pick 6/7. Or I can pick, I'll pick 6/7. Okay, so if we look at the numerator, a little bit trickier. I have 6 times 6/7 plus 5. My 7's cancel out. So I have negative 6 plus 5, which is a negative number. My denominator, I have 6/7. The key thing is 1 minus 6/7 is a positive number, because 6/7 is less than 1. So I have a positive number raised to the 3/5. It's still a positive number. Times 5, it's still a positive. So when I have a number between 5/7 and 1, I have a negative divided by a positive, which is a negative number, which means my derivative is negative in that little interval, which means my function is decreasing right here. And so same idea. For this region here, I just want to pick any number bigger than 1, 2, a billion. It doesn't matter. But the same idea. Let's go with 2. Negative 7 times 2 is negative 14, plus 5 is still a negative number. In my denominator, 1 minus 2 is a negative number. Raise it to the power of 3, it's still negative. Fifth root, it's still negative. It's all going to be negative. Negative divided by negative is a positive. And so my function is, again, increasing right here. And what I just did is this step right here, determine whether my function is increasing or decreasing. Notice I used my first derivative, but I didn't so much evaluate exactly. I just paid attention to are various parts positive or negative. All right, determine if there's any inflection points. If there's any inflection points, I need to look at my second derivative, which I have up here. And this will have inflection points anywhere my second derivative equals 0. So I can just tell by looking at this, this will equal 0 and my numerator equals 0. When 14x minus 20 equals 0. And that'll only equal 0 at 20/14. 20 divided by 14, or 10/7. So there's one inflection point. So I'll write that down. So 1 inflection point. That's when f prime equals 0. And that's at when x equals 10/7. And so now that leads me to the next point. Determine where my function is concave up or concave down. And so for that, let me make another number line here, similar to what we did before. But this time, in terms of concavity, all I care about is 10/7. So the only number I'm going to put on here, 10/7, which is more than 1. If I was to show the previous numbers, 1 would be about here, 5/7 would be about there. But in terms of concavity, all I care about is 10/7. And so like before, I can now pick a number that's less than 10/7, 0, put it into my second derivative. And again, all I have to do is really pay attention to the numerator. Actually, no, I don't. Take that back. Don't listen to me. But like before, just pick a number less than 10/7. I'm going to go with 0. And so if I put a 0 for x, I get a 0 right here. 14 times 0 minus 20 is a negative number. My denominator, 1 minus 0 is 1. To the power of 8, fifth root, 25, it's all going to be a positive number. So in the end, when I have a number less than 10/7, my second derivative is a negative divided by a positive, so it's a negative number, which means it's concave down. So all this region, concave down, all the way up to 10/7. Again, if it changed anywhere else, if there was another, if concavity changed anywhere less than 10/7, then there'd be another inflection point. But again, I can see from my equation there's going to be only one inflection point. Same idea for a number bigger than 10/7. Pick anything bigger than 10/7, 2, a billion, 6, whatever, 11/7. Put into the equation, you'll get a positive number, which means it's concave up for this whole area. And so now I know there's an inflection point, and I know not only is there an inflection point at 10/7, I know where it's concave up and where it's concave down. So lastly, determine the limits as we approach plus or minus infinity, and then we should be able to piece all this together to make a graph of my function. So first, if I look at my equation, make a little note right here. As x, actually I'll just write that in the limit. The limit as x approaches negative infinity of f of x. Actually, I'll write down the actual equation so I don't have to keep scrolling up so much. Well, as x gets infinitely negative, we have an infinitely negative number here times again a fifth root. The fifth root of a negative number is a negative number, and so as x gets infinitely negative, sorry, a lot of little details, but it is being squared. So as x gets really negative, this will be a negative number. This will keep getting positive, but there's no reason it's going to have an asymptote, and so this will approach negative infinity. And similarly, as x approaches positive infinity of this. As x gets really, really large, there's nothing to slow it down from getting really, really large. It's not being divided by x or anything like that. And over here, as x gets really large, that gets really large. So you have a really large number times another really large number is a really large number. And so now I know there's no asymptotes here. And so now at this point, all this information I have here essentially is the same sort of information I was giving you in the previous questions. And so now to piece this all together for a quick sketch, I'll kind of show that here. So what matters? Well, what matters to me are the points that I had shown those number lines. 1, 5/7 especially, and to some extent 10/7. That was that inflection point. And so at this point, this graph must look something, well, I can get the general shape. I can also just start picking some values for some of these, for example, at 1 or at 5/7. I can just take those values and put them into the original function to find the y values for them. For example, when x is 1, I know it's a critical number. When x is 1, I have 1 minus 1 is 0. which means I know the output is 0 at that point. And for 5/7, if I put 5/7 into here, I know it's some positive number. I know it's not 0. But right now, I'm more just concerned about the general shape, and so this must look something like this. I'll kind of sketch out what it must look like. So there's an inflection point. Sorry, there's a critical point there. There's a critical point here. There's an inflection point right here. Notice, if I look back up here, my function does not exist. Sorry, the first derivative does not exist at 1. That's why I drew a cusp. But my first derivative equals 0 at 5/7. That's why I drew something like this. I know it's increasing all the way from -infinity up to 5/7. That's why I drew something like this. I know it's decreasing in only this little interval between 5/7 and 1. That's the only region it's decreasing. And then it's increasing after that. I know it's concave down all the way up to 10/7. And if I draw everything you see here is concave down until right there, and then it becomes concave up. And looking at my limits, there are no horizontal asymptotes. So as I go forever to the left, it goes forever down. As I go forever to the right, it goes forever up. And so if you look at this, I'll just draw this darker now. If you look at this and go, that's difficult, I agree. And most students will agree with you. Especially when I just give you derivatives. And that means you have to use everything we've learned in the course, really, including limits, to figure out all these various characteristics of the function and then piece it all together. In this case, I'm dealing with 3 different functions, f prime, and f double prime, and see how they interplay with one another and affect the behavior of the graph. Yeah, that's complex. Which is why we're kind of going through this step by step. And that's why if we first are not developing our proficiency with questions like this, where you're just given all these characteristics, then we'll never be able to get really even started with questions like this. Because here we actually have to find these things ourselves. So hence, I've been starting with these sort of questions here, which are very challenging in their own rights. Okay. So with that said, that was a while, eh? I think it's time for me to stop talking.